two vector spaces, and that this theorem is somewhat related to what we had proved earlier, dimension subspaces. Okay, let me recall that we had seen this one, dimension of W1 plus dimension of W2 is equal, okay, dimension of W1 plus W2 plus dimension of W1 intersection W2. To prove that, we had considered the dimension of this thing, okay, and then we know the dimension of this and the dimension of W2, because W1 W2 we are given as a finite dimension subspaces, and then we subtract all these things, and then we just see that this is m plus n minus something k, and then we prove that this has a dimension of this. In a similar approach only, we are going to assume some of the things, and then we'll prove the rest of the other part. Okay, that's how we are going to do, because we are given as this finite dimension subspaces. Okay, w1 w2 are finite dimension if it is given, then w1 intersection w2 is also finite dimension. Using that concept, we had proved that w1 plus w2 is also having this dimension. Similar approach, but it's little bit different, because we will bring the concept of your null space of t and the range space of t here. Okay, so we'll just have this. Okay, so let's state that first. Okay, so we take as usual. Okay, we take let v and w. Let v and w be two vector spaces over f. Be okay, vector spaces over f, and let t from v into w be linear. Okay, be a linear transformation. Be linear transformation. Okay. Suppose that v is finite dimensional. Suppose that v is finite dimensional. V is finite dimensional. Then because you have to prove that the rank of t plus rank of t plus nullity of t is equal to dimension of p. Okay, let v and w be two vector spaces over f, and then okay, so t from v into w be a linear transformation. Okay, that's true. And then suppose that v is finite dimensional vector space. Okay, this all these conditions are usual condition only. Okay, t is a linear transformation, and then v is finite dimension. What we have to prove that you have to see this only, rank of t plus nullity of t is equal to dimension of t. So then we have to talk about the dimension of range space of t and then dimension of null space of t. That is the meaning of that. Okay, which is same as dimension of v. So this is other way of saying that dimension of range of t plus dimension of null space of t is same as dimension of the vector space. Okay, so now we are connected to the dimension. Now we need to no consider some of them, and then as usual, like we consider at least for this null space of t or a range of t, whatever. Okay, so maybe we consider for null space of t, because that's quite easy. So null space of t we consider, and then we'll proceed for your dimension. Okay, the other dimensions we'll just proceed. So because we are going to we can make use of two things what we had discussed earlier. Dimension of this one, the range of T is a subspace of, there are two things are given. Okay, let's have the proof. See, either one of them can be used. One thing that we know that one thing. Okay, so we know that first thing what we know that null space of T is the subspace. Okay, this is creating a lot of problems. Okay, so what we know that null space of T, null space of T is the subspace, is the subspace of V. And second thing, range of T is the subspace of W. This is what we had seen. Okay, these two things we had proved earlier. Nullity of T is the subspace of V and range of T is the subspace of W. But what we are going to choose this thing, null space of T is the subspace of W. Why? Because here it is given that V is finite dimensional. Okay, so nothing said about W, but W is also finite dimension. But in the hypothesis, nothing said about W. So since V is finite dimensional, so we can talk about the first thing. Okay, so we'll consider the first thing and then we'll make use of the second thing as usual. Okay, since V is finite dimensional. Okay, since V is finite dimensional, V is finite dimensional, V is finite dimensional. Subspace is also finite dimensional. So null space of T, which is the subspace of V, is also finite dimensional. Okay, I hope this is clear because it is a subspace. Null space of T is the subspace, and whatever subspace you take from that, that is also finite dimensional. Okay, so that is not an issue. So finite dimension means was V is the dimension of V is something and dimension of null space of V is something. Okay, but null space of T is a subspace. Okay, so what we choose is that suppose we choose this something is a basis. We have to choose one thing. We have to choose a basis for this as well as we have to choose a basis for this because both are finite. If both are finite, then we must there must be a basis for both of them because it is a finite dimensional. Okay, because it's a finite dimensional. So now we choose basis one and then the other basis also we can write it. So now we'll take, let us take, let us take something. Okay, u1, u2, u beta. Okay, be a basis for, be a basis for null space of T. Okay, u1, u2 to be a basis for null space of B. Since null space of T is finite dimension, if you want you can write this is finite dimension. Okay, similarly we can take u1, u2 to u beta. Okay, v1, v2, vm something, let's say, be a basis for v. Hello? Hello? Am I audible?
Yes, sir, you are audible.
Okay, okay. So network has gone, so I just use my mobile internet. Okay, so just if there is some problem, please let me know. Okay, so we had considered two things. One is that one is basis for null space of T, and the other thing is basis for range of T. The one question you may think about that, we had considered the common vectors. You see, u1, u2, u beta is the common vector. Why? Because the null space of T is the subspace of vector space V. So these some of the vectors must be common. So I just considered null space of T is the subspace of the. So whatever vector I consider for null space of T, that must be in V. Okay, that must be in V, and then say there are some more vectors. Okay, so therefore it is very clear that the dimension of null space of T is what? Dimension of null space of T, what I am getting? Okay, the dimension of null space of T I am getting as beta. Okay, the number of elements is beta. But what about the dimension of V? Beta plus m. Okay, there are beta vectors and there are m vectors. Okay, the number is beta plus m. So what we want to prove it, we have to prove that, okay, the dimension of the rank of T plus null space of T is equal to dimension of V. Okay, so therefore the dimension of V can be expressed as dimension of V can be expressed as dimension of null space of T plus dimension of range space of T. This is what we have to prove. But what we know from the previous, this is beta plus this dimension of range of T. But what I know dimension of V is beta plus m. So this beta is okay, but this m we don't know. So now I have to prove that only this thing. If we are able to prove that dimension of range of T is equal to m, then we are done. I hope it is clear. We want to prove these things. Dimension of V is equal to dimension of null space of T plus dimension of range space of T. Dimension of vector space is what? Beta plus m. And dimension of null space of T is beta. And we don't know this thing. Now beta is there here also. That is fine. So now only thing is that if we are proving that dimension of range space of T is equal to m, then we are done. So we have to prove that dimension of range of T is equal to m. Only if we prove this, then we are done. Okay. Or that is what you want to prove, that m is equal to dimension of range of T is same as rank of T. Okay, so that's what we have to prove it. See, again, as I told you earlier, so it is purely connected with your basis, because we are talking about a dimension. Okay, so then okay, so let us see that range of T. What is the range of T? So T is a mapping from V into W. Okay, so T is a mapping from V into W, right? T is a mapping from V into W. So range of T will be in W, right? That I know. The range of T should be in W. Okay. So therefore, what? Suppose I take the vectors V1, V2, etc., Vm. Okay. Suppose I want to take a vectors V1, V2, etc., Vn. So that the range of T will be what? T of V1, T of V2, etc., T of Vm. But I have to make sure one thing is that I have to make sure I have to keep it in mind. I should be having only m vectors. Okay. I should be having only m vector so that I can prove that that is a dimension. So now what I am going to take that we have to show that okay, tv1, tv2, etc., tvm is a basis for m is there here. Okay, we'll write clearly. Is a basis for range of t. So if I can able to prove that this is a basis, then I have a m vector 1, 2, 3, etc. This is one vector now. tv1 is a vector, tv2 is another vector, etc. tvm is a vector. So there are m numbers are there. So m vectors are there. So then if I can able to prove that this is a basis for range of t, then its dimension is m. Okay, so then I can have the conclusion. Okay, so again now we'll come back to the previous thing. If we want to show something is a basis, so there are two things. One is that the set is linearly independent. And then spanning set. Am I audible?
Yes, sir, you are audible.
Okay. So there are two things. One is that the set is a spanning set, and then it is a linearly independent. Okay, now let us see that first thing we'll just see that it is a spanning set. Let us now see this first observation. Let y belongs to range space of T. Let y belongs to range space of T. So what is the meaning of this? Then there exists some x is in V such that Tx is equal to y. This is by the definition of your range space of T. So y is equal now can be, but x is a vector is in V. Okay, V is a basis. X is a vector in V. V is a basis. So what is V here? Okay, now we'll see the number of vectors in V. See u1, u2 to u beta, v1, v2 to etc. vm. So this, if you take any vector, if you take in V, so that should be expressed as linear combination of these vectors because it is a spanning set. It is a basis. So therefore, if you take y is equal to tx, but x is a vector in V, so this can be expressed as T of x should be expressed as something like that. C1 u1 plus C2 u2 plus C beta u beta plus D1 v1 plus b2 tm vm. Okay, since we want to, you can write the reason. So these are the vectors u1, u2 to u beta, and then v1 to vm is a basis for V. Is a basis for V. So suppose, so you take any vector in that, so that should be expressed as linear combination of that vector. Okay. Now there is other ways, there is other condition is also there, and T is a linear transformation. Since T is linear, this T can be brought into inside. So therefore C1 is constant, C2 is constant. Those constants are also taken out. All these constants are taken out. So now T is linear. So y plus times T of u1 plus C2 times T of u2 plus etc. plus C beta times T of u beta. Okay. Similarly here, d1 times t of v1 plus etc. plus dm times t of vm. Okay. Okay. So this is what observation. This is since t is in here, we can just bring it inside. That's it. So we just brought it inside. So because this is a vector, so this is a scalar. So c1 is scalar, c2 scalar, etc. c beta is scalar. Similarly, d1 to d beta is scalar. So all those scalars can be taken out. So what I know that one more information I had. This